series. This is the second speaker in this quarter. We are very honored to have, by the way, this speaker series is created so that we can invite prominent leaders in computing, both from academia and industry and national leadership. And today it's really my honor to introduce Dr. Tsu-Jae Liu. She is currently a vice provost of academic and space planning at UC Berkeley, and she was a former EECS department chair at UC Berkeley, and also she's a TSMC distinguished professor in microelectronics. She has numerous awards, which I hope you saw from her biography, but notably she's an IEEE fellow and also a member of the National Academy of Engineers, which is very prestigious membership for almost like a most recognized recognition among engineers. So it's really my honor to introduce Dr. Liu, who's demonstrating leadership both in her research area of microelectronics and also leadership within UC Berkeley at the university level. So we look forward to her talk. Yeah.
Thank you very much. Thank you, Professor Kim, for that very kind introduction. It's always embarrassing for me to hear any long introduction because, as I think my faculty colleagues know, a lot of our accomplishments are really based on the work of our outstanding grad students. So I have been very fortunate at UC Berkeley to have worked with many good grad students. And together we have accomplished some significant work. And I'm just going to talk to you today about some of the most recent work coming out of my group. So the title of my talk is sort of plays off of a talk that Professor Richard Feynman gave more than 50 years ago. He was a Nobel laureate in physics, where he postulated what advantages could be derived from miniaturizing electrical and mechanical switches to be close to atomic dimensions in size. And so my presentation has two parts. The first part is just to show you that actually we're still a long ways from reaching atomic dimensions. There's still plenty of room to continue to miniaturize let's say, the transistor. And I'll explain to you what I think is necessary to continue to sustain Moore's law. Also, though, there are opportunities to add things over the transistors to further enhance the functionality of integrated circuits, one of which is shown in cross-section here in the background. This is a scanning electron micrograph that I took from online. It shows the cross-section of a Intel microprocessor chip. And most of the layers of features here are the interconnections, the wiring that is needed to interconnect the billions of transistors at the very bottom here at the surface of the wafer substrate. So I know that many of the people in the audience today are not electrical engineering graduates, so I thought it would be good just to make sure that I first review some basics of transistors and then talk about challenges for transistor scaling to the atomic scale limit. Then I'll talk about how we really can facilitate the sustaining of Moore's law. So Moore's law, I think, is still at least 10 years away. I mean, more left to go, and I'll explain why. But eventually, I think everybody agrees that we are not going to be able to sustain transistor scaling beyond atomic dimensions. So we need to start working on things beyond the era of Moore's law. So I'll give just one example of that today, and I'll conclude with a summary. So with regard to transistors, so the most advanced integrated circuit chips today have over 10 billion transistors fitting on sort of an inch square piece of silicon. A transistor fundamentally used in a computing chip just needs to serve as an electronic switch. So it has three terminals, a gate terminal, I'm just going to use my mouse here, the gate terminal to which you apply voltage to control current flowing between the source and drain terminals. Now, the source and drain regions of the semiconductor are heavily doped with impurities to make them electrically conductive. They have a lot of mobile charge carriers in them and can conduct current. But the central region in the semiconductor underneath the gate electrode is actually not heavily doped, so it's usually not conductive unless you apply a sufficiently large voltage on the gate above some threshold, okay, some threshold voltage. Then you can conduct current between the source and drain regions. And the gate itself should not conduct current it's electrically isolated from the semiconductor channel region by a thin layer of oxide. So this is hence the reason why this device is called a metal oxide semiconductor field effect transistor. You have an electric field induced when you apply a gate voltage to cause the channel to become electrically conducting. Okay, so the maximum voltage used on an integrated circuit chip today is on the order, is roughly 1 volt. So I'll just refer to this voltage generically as VDD. So depending on how much voltage you apply to the gate relative to the source, you can conduct more current in this transistor. So a nice simple model for a transistor would be a mechanical switch. However, if you look at the current plotted on a logarithmic scale, we can see that below the threshold voltage, the current doesn't just fall to 0. It does drop off exponentially. But when you have no voltage or 0 volts applied to the gate, there's still some non-zero leakage current that flows. So I'm just going to call this the off-state leakage current. In the on-state, when you apply the maximum voltage to the gate relative to the source, you can have some on-state current. So the ratio between the on current and the off current is usually many orders of magnitude. But really, if you'd like to reduce the voltage that's used to drive this transistor, you're going to have to, like, let's say if you lower VDD, you're going to have to give up something, either on current or you're going lower on current or higher off current. I'll come back to that in a little bit. So the way physically that a transistor works is that you have all these mobile electrons in the source region because it's heavily doped. Energetically, they're distributed exponentially. So the higher up in kinetic energy, the exponentially fewer electrons actually reside in the source region. So the way a transistor works is that you control a potential barrier for electrons to flow into the channel by the gate voltage. So as you apply gate voltage, you're lowering that potential barrier. So as you lower the gate voltage, the barrier lowers linearly, and the number of electrons that can diffuse into the channel increases exponentially. And this is why you have an exponential dependence of current in the subthreshold regime on the gate voltage. Okay, so that's the fundamental mechanism. So a switch is really more like a sliding switch, as I showed earlier. The more distance you move the gate voltage, in other words, the more you move that sliding controller, the bigger difference between on-state and off-state current conduction. Now, some of you might have heard that Intel was the first company to introduce a revolutionary transistor design. They call it the three-dimensional transistor structure. I just wanted to mention what that is. It is a fin-shaped transistor. So today now, people call this the FinFET technology, FinFET. And the FinFET was developed at Berkeley even before the turn of the millennium in the late 1990s. So back then, we demonstrated that if you can actually make the semiconductor not planar, but sort of three-dimensional, so it's a narrow fin, and that allows you to straddle have the gate electrostraddle the channel region. The gate has better control of that channel potential. And so the benefit here is that if you look at the current versus gate voltage characteristic, if the width of this fin is narrower than the gate length, so that's roughly a separation between the source and drain regions, then you actually can get good gate control, so you can turn this device on and off more steeply. So the benefit of that is that you can actually lower the operating voltage and still get your good on current as compared to before. So you get good on-off current ratio, but operating at a lower voltage, so you can save power. So this is why FinFET technology provides for either higher performance or lower power consumption in the most advanced integrated circuits today. So back in the early 2000s, we showed that the FinFET could be scaled towards 10 nanometers. Actually, a year after this, we showed that it was scaled to below 10 nanometers. And Intel first announced that they were putting this into production in 2011. And it actually appeared in products in 2012. My point here, pointing this out, is that it took more than 10 years, right, for our innovation to actually make it into a product, because all kinds of things are needed to make sure that this could be manufactured reliably and last for a certain number of years under a wide range of operating conditions. So that just means that the kinds of devices we're working on today are things that we envision will be needed more than 10 years from today. So let's just keep that in mind. Now, the height of the fin, so in a FinFET, most of the current flows on the sidewalls rather than the top of the fin. So the taller your fin, then the more current your transistor conducts. But from a manufacturing standpoint, it is not practical to allow the circuit designer to specify fins of different heights for different transistor strengths. So in order to adjust the transistor strength, basically the technique is to increase the width of the transistor, but in essence, increasing the number of fins. So the more number of fins, the more current that your transistor conducts. So this is the state-of-the-art technology used in the leading microprocessor chips today. So we saw an evolution from a planar structure, shown in cross-section here. We have a gate electrode, and the thin oxide is like 1 nanometer, and so you can't see it, but here's the semiconductor and then source drain regions. So evolution to FinFET. There's some companies that are looking at making a very thin silicon on insulator, so this is silicon dioxide under here. So same thing, the benefit of this ultra-thin body transistors to increase gate control. And this, anyway, so this helps to facilitate miniaturization. And, well, I'll explain, maybe I'll come back to why that facilitates miniaturization a little bit later. So the industry's next planning to evolve the semiconductor transistor structure into nanowires. So in order to achieve the best gate control, they want to wrap the gate entirely around the channel rather than just on 2 sides or 3 sides. So that's kind of next in the works. This is going to be more expensive to manufacture, but and the reason why we want to stack multiple ones on top of each other is really just to have a lot of current per unit layout area, just to have chip area efficiency. So that's kind of the roadmap for transistor scaling. Now, ultimately, though, we know that there's some limit to how small the gate length can be, and that's related to how closely spaced apart the source and drain regions can be. So here again is the energy band, the electron energy potential diagram. And it turns out that when a transistor is off, that means that it has to hold a voltage difference, or maintain a voltage difference between the source and the drain and prevent current from flowing. So that's why the potential is lower in the drain than in the source here. But if the source and drain come too close together, quantum mechanical tunneling through the semiconductor channel can occur. So if you look at the current on a log scale versus the gate voltage, if the channel is too short, then you can't really turn off the current very well. So that means this subthreshold slope starts to degrade, and you really start to see a lot of off-state leakage current. So there's some ultimate limit in scaling, and it's on the order of a few nanometers. But I wanted to point out that a team of researchers led by Professor Javi at UC Berkeley recently published a result where they showed a 1 nanometer gate length transistor, where the 1 nanometer was just the diameter of the carbon nanotube that was used as an electrode for this transistor. And the channel is a 2-dimensional layer of transition metal dichalcogenide. So this is molybdenum disulfide, it's an advanced 2-dimensional structure. So it has no dangling bonds. It's very thin, less than 1 nanometer thick. So they showed that actually if you can make the channel super, super thin, again, thinner than the gate length, then you can get a transistor, reasonably switching on and off, even at 1 nanometer. So we're still, today in manufacturing, the FinFET is like 20 nanometers gate length. So we still have a long ways to go to miniaturize the transistor with each new generation of manufacturing technology. So the computer scientists, you can count on more generations, more years of Moore's law to enhance performance. Yes?
Does the university own the patent on the FinFET?
So UC Berkeley does have a basic patent on the FinFET, and it has been licensed out. But that's one of the challenges. We actually are not getting much money for it, but it's okay. We at least get recognition for it. That was back in the days when the University of California wasn't, strapped for money. So it turns out then, maybe people already have read the news in our industry, but why? I mean, people have talked about Moore's law slowing down or ending. Have people heard that? Let me explain what that means. So actually, what is Moore's law? I figured most people know what Moore's law is, but what is Moore's law actually? Oh, the professor obviously knows. Okay, sorry. Any student want to? Yes.
So every 18 months or 2 years, we can double the density of transistors.
That's right. Yeah. So nowadays it's stretched out to every 2. Well, Gordon Moore updated it. So it's every 2 years. The most advanced chip available on the market has double the number of transistors on it. So roughly double the density. The chip sizes have grown over time. But fundamentally, the reason why, if you read Moore's original paper, the reason for that is because as the manufacturing technology advances, you can actually manufacture with higher yield smaller devices. So it makes more sense cost-wise. If you want to minimize the cost per transistor, it turns out you naturally want to increase the number of transistors on a chip as you advance the manufacturing technology. So as you refine the resolution limits of lithography, you can fit more transistors on a chip. And roughly the number of steps, the process steps needed to manufacture your chip, didn't increase dramatically from one generation to another. All you're doing is just increasing the precision of manufacturing of each step. So this made it cost effective. For roughly the same number of steps, not much increase in the cost, you double the number of transistors. So it makes sense to double the number of transistors on a chip. But this has changed recently because it's no longer the case that you can have roughly the same number of steps to manufacture double the number of transistors. And this is because of fundamental limits in lithographic patterning. So the process of lithography is where you use light, you shine light through a mask to pattern every layer, one layer of the integrated circuit. And as the size of the patterns, the size of the features of the transistor has shrunk below the wavelength of light, you can no longer really define such fine features with conventional photolithography techniques. So what the industry has done in recent generations of technology is to use what they call multi-patterning techniques. So they might perform lithography to pattern one set of features and then repeat the lithography process to pattern another set of features, sort of shifted over. This way they can get double the number of features with smaller pitch. But then you have to increase the number of steps. And lithography is actually one of the most expensive processes in the whole IC manufacturing process flow. So the industry has relied on what they call lithography etch. So lithography to pattern the mask and then etching it to transfer that pattern into the IC layer. They do that twice, litho etch, litho etch. So you increase the number of steps, you increase the cost. I'm going to talk about spacer lithography next. But in general, what was apparent years ago is that the industry was realizing, okay, lithographic patterning costs just growing geometrically, that is going to threaten Moore's law, because Moore's law is all about roughly the same number of steps, double the number of transistors. Here you're increasing the number of steps significantly to double the number of transistors. Now years ago when we were making the first FinFETs, the FinFET, as I mentioned, has to have a feature size, the fin width, smaller than the gate length. And that was not trivial because in the old days, the smallest feature on a chip was the gate length. So now how are we going to make something smaller than the smallest feature that could be defined by lithography? So we developed this so-called spacer lithography process, which has now been used in industry. It's one of the double patterning techniques that I'm going to talk about next. But we called it spacer lithography, as hopefully you'll understand why. But now the industry has called it self-aligned double patterning, or SADP. The idea is relatively simple. So even before resorting to this kind of a double patterning technique, as the feature sizes got smaller and smaller, the industry went to simpler and simpler patterns. Because imagine if you're trying to write something with a thick Sharpie, a thick pen, and you want to write something really fine. If you want to write some fancy script, it's going to be harder to do that. If you just draw straight lines, it's easier to draw really small features with a fat pen if they're just simple straight lines. So the industry already went, in the 2000s to very simple straight lines for many integrated circuit layers, just to make it easier to pattern them. So imagine that this is a cross-section of a straight line that we'd like to pattern. Okay, so let's say, imagine we want to make some straight fins. So the process here for spacer lithography is to deposit a dummy layer, a sacrificial layer. Sometimes people call it the mandrel, because you're going to form spacers around it. So in the past, we used silicon germanium, which could be selectively removed relative to the silicon, which is on a oxidized layer, thin oxide layer. Okay, so you use conventional lithography and etch processes to pattern the silicon germanium line. Then we deposit conformally another layer over that by chemical vapor deposition, or today it's atomic layer deposition. You can control this to be atomically fine. You can control the thickness to atomic precision. So notice that on the side walls, vertically is thicker than in the flat regions, right? So the next step is to perform an anisotropic etch process, where you're etching only directionally. So this way, we etch away the film on the flat surfaces, but since it's physically thicker along the sidewalls, then you form these spacers, or some people call them stringers. Then we can selectively remove the sacrificial material, and then use the spacers to pattern the fins. So this is how we pattern the fins for the early FinFETs. And notice you get two features for one lithographically patterned feature. So this is why it's called double patterning, because you end up with double the density or double the number of features. Now that's to form fins. You can actually also use double patterning to form trenches, like if you want to form like straight line trench features. So again, you form the sacrificial material with the mandrel. So this is the light-sensitive material, the photoresist that you expose through a mask. Use the photoresist to pattern the mandrel layer, then form the spacer layer over it, and do the anisotropic etch. Then you can actually do another layer of photoresist with a second mask. So now you have two masks to pattern one layer. You have all these steps to just form two trenches that are just straight lines. So you need two masks and all these steps to pattern one layer, one IC layer, whereas in the old days you just need like one mask and one etch. Okay, so this is just an example of how much more complex the processing is getting. Okay, so one thing that one of my students has done recently is, well, that's kind of expensive. Let's come up with a lower cost approach to double patterning. So the idea is relatively simple. You can look at let's say this is an IC layer you want to pattern, and let's say this is some hard masking layer, a layer that can be used as a mask to pattern this substrate. And let's damage it purposely by bombarding it with ions. But we can do it at a tilt angle. So if we form a mask on the surface of this hard masking layer, with a tilt, we can actually take advantage of the shadowing effect to create a damaged region, like a straight line, that has sublithographic dimension, right? So it's smaller than the minimum feature size that can be defined by lithography, which are these big, photoresist features. So it's pretty simple, right? The key is that we did some experiments looking at the etch rate of that hard mask, silicon dioxide, as a function of depth. And without an implant, the etch rate in hydrofluoric acid is very low. But with implants, depending on the dose, you can actually enhance the etch rate quite a bit, like by almost 10 times. So the idea here is, let's say you have some pre-existing features on the mask, so you want to double the density on the surface of the wafer. You want to double the density. These are just straight lines shown in cross-section. So you can do a tilted implant to achieve sublithographic damage regions, and then a second implant at the opposite tilt. And then you can selectively, more quickly etch away the damaged regions, and you end up with twice as many trenches, trench features as before. So we actually did proof of concept, just showing. So these are the hard mask features that were pre-existing. We did tilted implant, did some etch. You can see the sublithographic features here, smaller over there. And if you look at the plan view, top view, we started out with this white, mask layer. Did a tilted implant, so only this dark region was implanted, with that hard mask was implanted and etched. So you can see that the feature size is clearly smaller than the original trench, which is between these white layers. And there's the edge of this implant-defined feature basically tracks the edge of that originally hard mask. So proof of concept, positive and negative tilt angle, you can actually get two trenches where there was one originally. And the only reason I'm showing this slide here is if you look, well, because it's not perfect in the university, that original trench is not uniform in width. So we actually showed experimentally that this tilted ion implantation patterning technique could actually achieve feature sizes, this trench size smaller than 10 nanometers. Okay, so this is just a lower, okay, now let me explain now why it's cheaper. This shows the process steps I went through before for spacer lithography. Okay, you got to go through all these steps. With a tilted ion implantation, you don't need to have this hard mask. You instead of deposition and etch and so on, you just do two tilted implants. Turns out ion implantation is today one of the cheapest steps in the process and is one of the most precise steps also. So from a manufacturing perspective, this is saving the number of steps lowers the cost, and the type of step also matters. So if we do a cost analysis, bottom line, depending on your assumptions, you save about half the cost of patterning, double patterning, by using tilted implantation. So this is just an example of innovations that can help to extend the era of Moore's law, because it's really not physical limits of the transistor scaling, it's really the cost of manufacturing. So if people here working in chemistry or material science, you can come up with more ideas to simplify the manufacturing process to lower the cost. Still plenty of room at the bottom for transistors, to fit more transistors at the bottom. Okay? Now, taking a different tack, let's go back and look at the impact of Moore's law. As we fit more and more transistors on a chip, the chips have become more functional, lower cost per function. This virtuous cycle where this enhanced functionality, better performance, lower cost has driven market growth, and the industry has reinvested some of its profits into further advancing the technology to enable this virtuous cycle for the last 50 years. So one way to look at Moore's law is the impact of Moore's law is to look at the number of computing devices that have been manufactured over time. And you can see that the number of computing devices has grown exponentially over time. And the functionality, let's say for your cell phone today, that is much more than a computing device. Right? So that's represented by the size of the circle. So as I mentioned, for researchers, we are supposed to be looking at what the industry is going to want or need more than 10 years from today. So that means we need to extrapolate more than 10 years. And well, that means that, and we're already seeing the emergence of the Internet of Things, but eventually within the next 20 years, we would expect on the order of 1 trillion computing devices in the world, right? Now, most of these are not going to be devices that we personally interact with, like our cell phones or computers. They're going to have to be embedded in the environment, in us. In other words, then, they're going to have to be very low power because we're not going to be able to change the battery or plug them all in. So a challenge for realizing this vision it's one thing to sustain Moore's law, but we need to have some products, some market, some profit to sustain this cycle. So the key here is low power, right? So in the future, what we think now for future device research is really to come up with devices that are much more energy efficient than the transistor, the FinFET that I showed earlier. So let me explain what the fundamental limit, energy efficiency limit of a transistor is due to. So you might have heard of CMOS technology. So this is short for complementary MOS technology. So a transistor circuit symbol, it's a stick symbol that's shown here, gate that controls, that's electrically insulated from the source and drain, controlling current flowing between the source and drain. Now there's two flavors of transistors. One when it turns on with negatively charged channel. So that will only turn on when you have a positive gate voltage to attract the negatively charged carriers to the channel. The other flavor is a P-channel MOSFET. That turns on when you attract positively charged carriers to form the channel between the source and drain. And that only turns on when the gate voltage is more negative or less positive than the source voltage. So these transistor types operate in a complementary fashion. If you tie the gate electrodes together and you tie the source of the N-channel MOSFET to the lowest potential, but the source of the P-channel MOSFET to the highest potential, then you can have a complementary circuit. So the drains are together driving the output node in this simple inverter circuit. So let's say in a static configuration, let's say you have 0 volts at the input, so there's no gate to source voltage on this NMOS device, but the gate voltage for the PMOS device is lower than the source voltage, so the PMOS device will be on. And yes, right, so this is the configuration. So basically the output will be connected to VDD, so the output will be high when the input voltage is low. Okay. Now, if we switch the input, if we make the input high, now we turn on the N-channel MOSFET, and the P-channel MOSFET turns off because now there's no voltage difference between the gate and the source. Now the key here is in either state, I should go back, right? In this state, the P-channel device is on, so it will conduct whatever current the circuit wants to flow between the source and drain. The N-channel device is off, but it has leakage. So that means even if the CMOS circuit is not doing anything, there's leakage current flowing between VDD and ground. So there's static power dissipation because the transistor is not a perfect switch. And in the other configuration, it's the leakage current of the P-channel device that is going to result in static power dissipation. Right? So there's always, even if your CMOS circuit is not performing any function, you're wasting power. And I think most of you probably know you can have more functional circuits by connecting transistors in parallel or series to perform logic functions. And then a memory cell just has two cross-coupled inverters like this. So you have two stable states, 0 on the left or 1 on the left. And you can access them through some access transistors. So a static memory cell comprises 6 transistors. So this is sort of the basis of CMOS digital computing. But the key here is that leakage current of the transistor ultimately limits the energy efficiency of a device. And for Internet of Things devices, most of the time those devices are off. They're not computing all the time. They're very low duty cycle. So it's really important to have as low of a leakage current as possible for Internet of Things devices. And those are the ones that are going to be like numbering in the trillions, right? So my group has been looking in recent years at mechanical switches, so revisiting mechanical computing. And the reason for that is because in a mechanical switch, in the off state, you have an air gap between the source and the drain electrodes. And to turn on, so you don't have the static power dissipation problem that transistors do. So it is a perfect switch in this regard. To turn on a electromechanically actuated switch, you apply voltage to the gate that induces electric field and that has some electrostatic force. And you can design this beam to be compliant. So you can bring the source into contact with the drain. And when you remove the electrostatic force by lowering the voltage back down, the spring restoring force of that structure will pull it out of contact. So you can actually turn on and off. This is measured data. And the on state, we purposely limited the current to 10 microamps because we didn't want to have this junction weld by keeping it running on all the time. But basically, you can see we're going from a gate voltage of 0 to a gate voltage of 100 millivolts. So that's 0.1 volts. And we can turn on this switch, orders of magnitude on and off. So basically, due to stiction, I think I have that here, when it's in contact, there's some adhesive force. So that's why there's always going to be some hysteresis. And part of our research is to actually look at coatings to reduce hysteresis. And we've actually recently published a paper showing hysteresis well below 50 millivolts. So we are aiming under funding from the National Science Foundation to develop mechanical switches that operate well below 0.1 volts. And that is below what a transistor would operate at. I forgot to mention earlier that subthreshold swing for a transistor, theoretically, it cannot be better than 60 millivolts per decade at room temperature. So if you want 6 orders of magnitude difference between on and off current, you need at least 0.36 volts of gate voltage swing. Right? So you can't really lower VDD to 1.1 volts and have it operate properly. The on-off ratio will be like 10. But here with a mechanical switch, you can have perfect on-off switching, no leakage, operating it with very low voltage, so you can actually have not only 0 static power consumption, but also very low dynamic power consumption, because lower voltage, that means less charge needed to charge and discharge the nodes in the circuit. Okay, so I don't know if nobody's here near remembers mechanical computing, but maybe you do. Okay, so there are some reasons, though, why the industry does not use mechanical switches for computing. So what do you think are those reasons? Yes? Hard to manufacture, okay, maybe. But if we leverage the integrated circuit manufacturing techniques that have been refined over the last 50 years, that's kind of what we're taking advantage of. But yes, maybe in the past it was hard to make them smaller to be more energy efficient. Huh? Fatigue, reliability, that's right, okay. Yeah, speed. How fast can you turn it on and off? A transistor, you can switch it on in less than a picosecond. You can get electrons to go from source to drain in less than a picosecond. Here, it takes time because of the mass to accelerate that structure and get it into contact. It's not going to be faster than like 100 picoseconds, right? So it's orders of magnitude slower. All right, very good. So nevertheless, for some applications for Internet of Things, maybe the speed of 100 megahertz might be good enough. So mechanical computing could be good for some applications. But yes, indeed, there are these fundamental challenges. How many times can you turn on and off before it fails? It's probably, depending on the operating voltage, but it probably will not be infinite. Okay. And yeah, hard to manufacture with small dimensions. That's if you compare mechanical switches to logic switches, like used for computing. But there are other types of transistors used for memory, like storage, non-volatile storage of information, like 3D NAND and so on, flash memory. Now, if you compare a mechanical switch with a flash memory device, then the picture is different. The amount of time it takes to program or erase a flash memory cell is actually longer. And these are more advanced memories like resistive RAM, magnetic tunneling junction in the upper right, ferroelectric random access memory, and So basically, the emerging new and non-volatile memory devices that are being published today and being explored are slower even than a mechanical switch, which is on the order of 1 to 10, maybe 10 nanoseconds to be very conservative. Another thing that's important to point out is that amount of energy needed to change the state of a mechanical switch to turn on or off is orders of magnitude smaller than the energy needed to program a non-volatile memory device. So a non-volatile memory device, usually you need to apply voltage, allow some current to flow to change the state of the cell. For a mechanical switch, you actually don't need to flow any current. So you could just have this drain voltage like floating, electrically floating, while you apply voltage between the gate and the source to get the gate and the source, the source to come into contact with the drain. No current is flowing between the gate and the source. So for that reason, you're charging up this gate capacitance, which has an air gap, which is low permittivity. So low capacitance, no direct current. This is the reason fundamentally why a mechanical switch is much more energy efficient than any other type of non-volatile device. Now we can easily engineer a mechanical switch to be non-volatile by having the surface having the compliance of the structure being very low, very high. So it's very flimsy. It'll just stick when it touches. So it turns out then, to address the manufacturing challenge, if you look at the progression of technology advancement by the integrated circuit industry, the semiconductor industry over time, we've evolved the transistor structure to FinFETs, but at the same time, the number of layers of metal wiring needed to interconnect all of them, all of those transistors, has increased, and the materials have changed in the back end of the process line. And if you look closely, to minimize, as the transistors get more tightly packed together, the metal wiring spacing also comes closer together. But that means you have more and more capacitive coupling between one interconnect wire and another. So what the industry has done recently is to introduce air gaps. So in Intel's most advanced technology, they actually have air gaps between metal lines in a couple of the layers. So what do you need to do? What kind of materials do you need to make a mechanical switch? You just need like conductors and an air gap to allow movement. So you can just leverage this to make mechanical switches just during the manufacturing process of a regular IC chip. You just have to design the air gaps and maybe do a final etch to release that little beam. So here's an example of a switch design. This is a simulation, obviously, where you leverage multiple layers of metal interconnects, and you can have actuation electrodes on the left and to the right. And depending on if you're applying a voltage between the movable structure and the left actuation electrode, you can actuate it to the left, or you can actuate it to the right. So this is the concept here, that you can program a mechanical switch. And again, the contact electrodes up here, these are the current conducting electrodes. They can be electrically floating during the programming process. So no direct current flows. That actually allows for more reliable operation of the switch. So you can avoid welding. Okay, so because of limited time, I'll just show you one example of how this could be useful. Okay, so we want to leverage the low energy benefit of a mechanical switch, but it's slow. So basically, one way we can have very low energy computing is to actually not compute at all, right? Just look up the answer, right? So people, in the old days, you could just look up the answer for some computation. So we can implement a lookup table with this kind of technology where you program an array of switches to perform the function that you're looking for, right? So here's just one example. So here's a circuit diagram of an array of these switches, okay? And these diodes, metal semiconductor diodes, just only ensure that current flows one way for the circuit to work properly. But anyway, here's a switch. You can either touch an electrode at the top, a 0 or a 1 electrode. Each of these switches is switched to left or right, and they're arranged in an array like this. And you have like horizontally running across this array a bit line, okay? And there's an input portion of this array and an output portion. So the first part of this, to use this kind of a circuit, you need to have an input portion and an output portion, but you need to electrically isolate them for part of the time. So this is where the CMOS circuits that are underneath can be used. You can connect them to form like a tri-state buffer. So you can actually disconnect the input portion from the output portion with the CMOS circuit. Then you can go ahead and program, so you can apply voltages to set the state of every switch to correspond to every possible combination of input bits. So in this simple example, we have an input string of five bits. And then the output has 2 bits. Okay, so each bit has a pair, a low and a high line. So you can read differentially whether there's a 1 or 0 stored. So once you program all the answers in, you can perform a lookup operation. So the idea here is, let's see if I have it. Okay, so you you drive the input lines here vertically, right here. So you apply voltages here. And, you first pre-charge the input and output lines. So pre-charge all the output lines high, and then pre-charge all the input lines low. Okay, output lines high, input lines low. Okay, then you input the input data. Okay, so here's your input string. So that means for each pair, you drive one line high. So it just turns out that if you program the switches properly, the input data line, or bit line that corresponds to this input string, that is the only line that remains low. Okay, so here's the input string, 00001, and only this one remains low. Then the next step, that's because the switches make connections to pull up the voltage on the other input lines. Then you turn on the CMOS tri-state gate so that only one of the output lines is driven low. That discharges the appropriate, one of each pair of the output lines. So then you can actually read out the output. So this is just an example of how you can just perform a lookup operation really simply. And it turns out that if you compare this with the way that you implement a lookup table with CMOS transistors, where you actually have to do this lookup operation in SRAM, but then you store the answers in a non-volatile chip off chip. So you have to move the answers from the non-volatile chip onto this SRAM chip and then actually do the operation. Turns out that if you do this with a simple non-volatile array of mechanical switches, the amount of area needed, going out towards the outside is better exponentially. The amount of area for the function is lower. The speed at which you can look up the answer is orders of magnitude faster. The energy needed to read out the answer is also orders of magnitude lower. So the disadvantages of mechanical switches being slower, bigger, and so on, those are avoided by using the mechanical switches in an intelligent manner together with CMOS. Okay? So I have another example here, but I'm not going to have time to show it. But if you're interested, I can tell you about it. So bottom line is, if you are willing to innovate together architecture as well as devices together, then you can actually get improvements in performance as well as in energy efficiency and cost at lower cost. So instead of transistor scaling in the future, eventually such kinds of innovations, like I've shown you here, will allow the Moore's law effectively to continue, so that we can see even more revolutionary impact of information technology on society. So as we all know, if you have trillions of devices, embedded, you have sensor networks and so on, smart sensor networks. You can do things to reduce energy consumption. You have automated driving, but improve traffic, which was actually not too bad here this morning. Personalized healthcare, monitoring devices embedded in us and deploying medical care when needed. We have earthquakes in California, so if we want to embed sensors everywhere in structures, we can monitor the integrity of structures and deploy emergency services where they're needed most urgently and let people know when it's safe to occupy a building. Of course, we want to always monitor the quality of the air and the water and so on. So, trillions of devices in the future that are all wirelessly interconnected, they're going to need to have some basic functionality, but the key is lower power consumption. And I think this vision can be realized with innovations such as the ones I've had just a little bit of time to share with you today. So that's pretty much my message, and I'm happy to take any questions at this time. Thank you.
So the old electromechanical relays were electromagnets, and that was the magnetic force.
Yeah, so you have current flowing
Is the same
and
thing
actually.
going on here, or is there something different? What's opening and closing these switches?
So it's really just a physical contact, right? So except you use electrostatic force instead of magnetic force to get it to switch one way or another.
So it's
So-
just a Coulomb attraction and
Yep,
repulsion.
Coulombic force. Yep.
And it works because they're so tiny that you can.
Yes. So it turns out the smaller the gap, the more. So the smaller the spacing between your actuation electrode and the movable electrode, the higher the electric field. So that makes the voltage needed even smaller. So as I mentioned before, we've demonstrated circuits, switches operating with below 50 millivolts. And our goal is actually to demonstrate 10 millivolt circuits, which at room temperature or any temperature. Actually, mechanical switches are nice in that they operate over a wider range of temperatures. They always have zero leakage, whereas with a transistor, if you increase the temperature, the leakage goes up exponentially. So a lot of advantages of mechanical switches.
So you charge them oppositely if you want them to close, and you charge them the same if you want to pull them open.
Actually, no. It's always electrostatic force is always attractive. So here, to get it to switch from one position to another, we have to actively actuate it to the left or actively actuate it to the right. Or the original simple design I showed earlier, you just rely on the mechanical spring restoring force. When something deforms, it actually has a spring restoring force. It'll just naturally want to pop back up, if there's no electrostatic force holding it down. So you can either rely on spring restoring force to turn it off, or you can actually add another electrode on the other side to pull it off. Yeah, it's always attractive. Yeah.
So I have some question about the damping effect. So you told that when once the electrostatic force is gone, it comes due to the spring effect, it goes up. But does it have damping?
Yes, so damping, air damping, yes, so that can slow down the speed, but so that's why I'm saying that the switching speed will not be really better than 100 picoseconds, more like a nanosecond because of damping and so on. But for certain applications like the one I showed you, the switching speed of the circuit, of the mechanical switches doesn't limit the speed of the circuit. You just set it. And the nice thing is for machine learning or whatever, you might want to update the output over time, right? So you can easily update the settings of the switch over time as your system is learning and just reconfigure the answer, right, over time. And it's very low energy needed to change the state of those output switches to change the answer.
Part of my question is that so this mechanical bead comes and physically touches the copper electrode.
Yes.
How good is the contact for the current flow?
Yeah, so we haven't actually made it with the conventional copper and actually the liner material, so it's like tantalum nitride or ruthenium in the future. But typically for this, as long as the contact resistance is less than 10 kiloohms, it's fine. If you think of a transistor, a minimum width transistor, when it turns on, it's conducting 100, let's say 1 milliamp per micron width. And a transistor today is less than a tenth of a micron width. So that's so that's 10 kiloohms in the on state. Right, so a transistor when it turns on is also kiloohms or 10 kiloohms. And so, so the idea here is you don't really need intimate contact. As long as there's contact so current can flow, you can detect if it's touching to the left or right. That's the nice thing about a mechanical switch. If it's not touching to the right, there's no way that any leakage current can flow there. So you cannot mistake the state of that switch. It's either going to conduct some current or no current. So it doesn't have to be amps. To save power, you want to detect microamps or less. So that means the contact doesn't have to have very low resistance. And actually, that is good for ensuring good reliability. Because the more intimate the contact, the more likely that over time it'll stick and fail, right? I mean, you can't switch it anymore. Yes?
Can the mechanical switch used in any kind of analog circuit? It's not very suitable.
Yeah, it's not good for that. It's not good for analog circuits. But it's easy for the designer, a circuit designer. You can draw the dimensions of the switch, like the length of the beam, perhaps. So you can adjust the stiffness. So therefore, you can adjust the switching voltage. So it's for a CMOS technology, the circuit designers, you're pretty much stuck. The threshold voltage is like 0.2 volts for high performance and then 0.5 volts for low power, something like this. So a circuit designer has no choice of the threshold voltage of their transistors. They're just given like a few choices to design with. Here, you can just draw like a different length beam, and you can actually change the switching voltage of your switch. So it gives more flexibility for circuit designers. So we've actually demonstrated that if you design arrays of switches that switch at different voltages, then you can do like an A to D converter, right? Because depending on the voltage, a certain number of switches are going to turn on depending on the threshold voltage. But generating an analog signal might be hard. But yeah, I mean, I guess any of these inputs, you could think of it as having an analog input signal, or rather than a digital signal.
So is there anything like magnetic force driven mechanical switch?
Yeah, so we did look at miniaturizing magnets, and it turns out that there's some fundamental limits for magnetic devices when you really try to make them nanoscale. So it turns out that they cannot generate enough force to actuate these devices, unfortunately. Yeah.
Your new question has enhanced etch. So I'm somewhat concerned about the effects of the dopants left over from your implants on the device.
Okay. So
What sort of dosage is required to enhance this etch? What sort of dosage would be low enough to not have an effect on the device?
that's a good question. So I sort of skimmed over that. The implant species is argon, so it's inert. And also the implant dose is in the mid 10 to the 14th per centimeter squared. And that, like typical dopant doses for the source and drain regions of a MOSFET in the old days, is like 10 to the 15. So this is a moderate dose. It's relatively low dose. And it's certainly, if you do a gentle thermal anneal, you can anneal out the damage to any underlying layers. But ideally, this is a very low energy. It's only 1.5 kiloelectron volts. That's relatively low. And this is a relatively thin film, 50 angstroms, so 5 nanometers. So the implant is really contained pretty much inside that thin layer. So very little damage occurs to the lower layer down there that's being patterned. Yeah. Yes?
In the mechanical switch that you showed with built out of the air gap vias, are there any additional process steps that you need to realize that switch? Or
yes. So that's some research that we're doing. We actually have laid out some of these back end of line NEM switches with a couple of companies now, and we want to work with some advanced foundries in Taiwan next. But yes, we would basically, the upper layers of metal we can lay out to form a mask for the etch. So yes, we need to do another etch to remove the dielectric completely along the sidewalls to allow that middle electrode to move. But the MEMS industry has already developed packaging techniques where you can then subsequently cap this and then proceed with the wafer or the die with a conventional packaging process. So it's not going to be very expensive to properly encapsulate these devices to allow some sort of vacuum conditions inside the air gaps. But you're right. Some extra etch and capping step will be needed.
do you prefer vacuum or air?
As long as it's not oxidizing, that would be the best, right? So you want something inert. So the vacuum is inert, but argon or nitrogen would be inert as well. Yes.
I was wondering how sensitive would your mechanical switch to vibration?
Yeah, that's a standard question. Okay. I didn't include the slide here. So the nice thing about miniaturizing mechanical switches, see, when you miniaturize a transistor, it becomes harder and harder to make it ideal because the direct quantum mechanical tunneling. With a mechanical switch, as you miniaturize it, the operating voltage comes down because the air gaps are getting smaller, but the mass of this movable structure goes down also. So the amount of force needed to actuate it left and right is on the order of like nanonewtons minimum. And if you can do a simple calculation to get a nanonewton of force with a mass that is like picograms. You'll need like 1 million Gs, gravitational constants, to accidentally, if you drop it or shake it, to get it to actuate unintentionally. So because of the smaller mass, it actually is very insensitive to, immune to vibration and shock. So you can drop it, shoot it out of a rifle. Those levels of shock are not going to be high enough to cause this thing to switch unintentionally. Great, good questions. Thank you very much.